An electric motor is a device for converting electrical energy into mechanical energy in the form of rotation. It uses magnetism to create electricity in many different machines. In everyday life, we use many machines and appliances that are supplied with electricity by electric motors. For example, one of them is a boat, a car, an electric toothbrush, a hairdryer, an airplane, and a washer dryer, and so many other appliances. To build our electric motor, we used a coil of copper wire, 2 paper clips, a rubber band, battery, pieces of sandpaper, and 1 magnet. We bent the paper clips into shape so they would attach to the battery under the rubber band and hold the coil. The paper clips were also conductors for electricity to travel from the battery to the coil, causing the coil to spin. We used the copper wire because it has permanent magnetic properties, which means it's attracted to other magnets. We shaped it as a circle and placed it close to the magnet because the closer to the magnet, the stronger the magnetic field and the faster it will spin. The battery acted as the power source for our electric motor. We used sandpaper to entirely remove the insulation from one side of the wire so that it is always in contact with the battery through the paper clip. The reason to remove half the insulation from the other side of the coil is so that the coil is only active half the time. This way, the coil and magnet push against each other without them pulling each other half the time, causing it to keep spinning. We used a magnet to supply a magnetic field for the coil to spin, so that it repels the magnet half the time and attracts the magnet the other half of the time. We wrapped the rubber band around the battery to keep the paper clips in place. By using the right-hand rule, which states that if you curl your fingers in the flow of the current, the north magnetic field will be in the direction of your thumb, we can determine that the direction we need to face the magnet to get the loop to spin will be repelled by the magnet and spin, and the insulator will then stop the flow of electricity, allowing it to continue to turn. If we don't do this, it locks in place. The coil is pointed diagonally, the north side facing the south, and the south side of the coil facing the north. This is because opposites attract. This causes the coil to twist. The magnetic field present is shown by the purple arrow on the diagram. Once the opposite poles align, the magnetic field is no longer present. This causes the coil to complete the rotation of a full 360 degrees. The magnetic field present should be maintained until the coil's opposites are attracted, which is shown in the diagram with the red line. The magnetic field comes back when the like poles align because they repel each other. It's important to turn the magnetic field off because once opposite poles align, the coil will stop turning. So when you turn it off, it will complete a 360 because like charges repel. The forces that are present on the copper wire when the current is not flowing through it is the force of gravity downwards from the earth and the normal force from the paperclip upwards. The forces that are present when the current is flowing through the copper wire is the force of gravity from the earth, normal force from the paperclips, the force of magnetism downwards, and the force of magnetism upwards.